Hi everybody, it's Dr. Chabot, and we in this video are going to talk about the electric field that is created by a dipole. So I have a rough sketch of what the electric field around a dipole looks like. And again, remember, electric field lines come away from positive and they point in towards negative. Kind of describes this entire space. At any point in this space, we would get the total electric field by simply adding the electric field from the positive charge plus the electric field from the negative charge. We have to do the vector addition to add those electric fields. Each dipole electric field can be found from the electric field equation for a point charge that we saw earlier in this module. So what we're going to do now is really, in order to describe the electric field and calculate it, we're just going to pick 2 points to look at. And so the 2 different points that we're going to look at is we're going to look at one of the points that is along the axis of the dipole and say some distance z away from the center. Or actually, I'll call that one x away from the center just because of how I have it oriented. And then I'm going to have another point that we're going to put along the perpendicular bisector, and we're going to put that one a distance y away from the center of that. So if we're just going to pick those two points and do the math in order to figure out what the electric field looks like at these points around the dipole. All right, so let's go ahead and just start with point 1. So what I'll draw out again is just this dipole where I have minus q, and then I have a plus q, and then I have a point P that's going to be over here, a distance x from the center of the dipole. And so remember that the dipole is separated by a distance d. And I'm basically just doing vector addition, right? I want to draw my free body diagram in order to visualize the vectors that I'm adding. So at point P here, I'm going to have 2 fields. I'm going to have the electric field that is from the positive charge. So I'm going to have an electric field from the positive charge, which I'll call E positive, and it points away from the positive charge. I don't even need to have a point. There's no charge at point P. I'm just looking at that point in space, right? And if I'm just looking at that point in space in order to decide the direction of the electric field, I'm remembering that the electric field points from positive, away from positive, and towards negative. So it's going to be pointing away from the positive. And then I'm going to have the electric field that's going to point towards the negative. And I'm going to draw this arrow a little bit shorter because the negative is slightly farther away. So those are the 2 vectors I'm adding. So it's actually just all, no real components because I just have my x direction. We'll take positive x to be in the direction that it usually is, to the right. And so now I can write out that my E total at point P is going to be equal to the magnitude of my electric field from the positive charge, and then minus the magnitude of the electric field from the negative charge. And that just comes from that free body diagram that I drew. And then that's all going to be in my x hat direction, also sometimes called the y hat direction. I don't have a y or z component at all to deal with. So now I can go ahead and just use the equation I have for my point charge. So that's going to be k and then q over, and then now the distance from point P to my positive charge is going to be x minus d over 2. And so that bottom term for that r is going to be x minus d over 2 quantity squared. So that's the contribution from the positive charge. And then minus k q over, and then the distance to the negative charge, we can see that's going to be x plus d over 2. And so that's going to be what's down here, x plus d over 2 quantity squared. And so that is, the general solution. So this is going to be true for all x. And so at first that might not feel too useful because it just looks messy, right? What we do know is that for all x, it does point in the positive x-hat direction, right? We do see that the net electric field here along that direction will be just in the positive x. But the magnitude, right, really has kind of this strange dependence. But what we can do is that we can show, and I'm not going to do it explicitly here, but as a challenge homework problem. If you remember that there's the challenge track, you're welcome to take this option as one of the potential challenges. But we can show using the binomial expansion that we can say that if x gets to be much bigger than d. We don't want x to go to infinity because then obviously the electric field goes to 0. But if it's just big relative to the dipole spacing, then we can show that the electric field along that dipole at point P is going to be reduced to the simpler expression of 2k qd over x cubed. And then that's going to be in the x-hat direction. And so note that this goes as 1 over x cubed, or it goes as 1 over the distance cubed, not 1 over r squared like a point charge. What's very interesting about that is that means that if you're far away from something and you measure the electric field, and you don't get 0 because you're not infinitely far away. If you measure the electric field and you see how it depends on distance, if it goes as 1 over r squared, that something is a point charge. If you measure it as 1 over r cubed, that something is a dipole. So you can actually have insight into the charge distribution being very far away with this result. Okay, so let's now go ahead and look at, I'll call it, say, point Q. So let's label this one point P. We'll label the one that's along the perpendicular axis point Q. So we'll do, say, at point P. And now we're going to dive into at point Q. So I'm going to redraw my dipole again, and here where I have it, I have the minus here, and I have the plus here, and then I'm going to have that separation again as D, and I'm going to pick my point P, and I'm going to call that some distance y here along that perpendicular bisector. So now it gets a little bit messier because I have to actually go ahead and visualize the distance between these. So we can see that I'll just call this for now a distance r, and my distance r for both of these is simply going to be the square root of y squared plus d over 2 quantity squared. And I probably also want to define an angle here, theta. And this is just like what we did when we added force vectors, where we want to visualize the vectors that we're adding. So now I'm going to, say, draw the free body diagram, and I had accidentally called this point P, but now we're looking at point Q. So the free body diagram at point Q, where I'm going to be visualizing my vectors, right? That's what we mean by a free body diagram. So I'll just say that always the second step is to visualize the vectors. And so at point Q, I'm going to have a vector that points away from the positive. So I'm going to have an electric field that points away from my positive charge. So that's my electric field from the positive. And then I'm going to have an electric field that points towards the negative. So I'm going to have an electric field here that points towards the negative. And then I had defined on this some angle theta that I recognize is the same as that other angle theta in my original diagram. So what we can see is that from this, my net electric field is actually going to be in the x direction, right? So I don't have to worry about any of the other components, and I can just add up my x components. So what I want to do now, right, is find the magnitudes of the vectors. So I can say the magnitude of E positive is simply going to be equal to KQ over, and then it's this R squared. So I'm going to just leave that as R squared for now. And that's also equal to the magnitude of the electric field from the negative, because they have the same charge on them and they have the same separation to my point that's up in space. I realize I called that point positive Q, and it is not a charge, it's just a point in space. I could have called it like P2 instead of just P or Q. So it is just a point in space. And so I have that electric field at that point in space. And so now those are the magnitudes, but now I need to add the components. So now I always do my next step where I find the components of each one. I cannot add vectors without worrying about components. So I can see here that I'm only going to worry about the the X component. So I only care about E sub X, so I don't actually have to make the whole table for E sub Y. I can just then say here that E total is going to be equal to negative magnitude of E plus times the cosine of theta, and then minus magnitude of E minus times the cosine of theta. So these are the X components of both of those vectors in terms of their magnitude. The negative sign is because they both point to the left in the negative X direction. So that's just me doing my components, plus or minus, sine or cosine, and putting it together. The other thing I can note, just like we did with forces, is that I can write the cosine of the angle in terms of the sides of the triangle. So I wasn't explicitly given theta in this problem, so I need to translate theta into the sides of the triangle. So cosine of theta would equal the adjacent, which is d over 2. So this is my triangle that I'm drawing, the shading triangle that I'm shading up here. So d over 2 adjacent over hypotenuse, which is r. And that r is that square root of y squared plus d over 2 quantity squared. Okay, so putting this all together, then I can say here that E total is going to be equal to negative KQ, and these are going to be the same. So what I can actually do is just double this. I'm going to keep this simple. I'm going to say 2 times, then I'm going to write it out one time, KQ over r squared, which is the square root of y squared plus d over 2 quantity squared, whole thing squared, right? And then times the cosine of theta, which is d over 2, times, again, the square root of y squared plus d over 2 squared. Now I'm just going to simplify it a little bit. I can see that my 2 and my d over 2 cancel. And again, this original 2 came from identical components. So instead of separating them out as two terms, I combined the two terms into one. And then I can write this as negative, and then parentheses k, q, d over, and then this is y squared plus d squared over 4. I've just worked out the d over 2 quantity squared, all to the 3/2 power. And that direction is in the negative x direction here. So we end up with this as our total electric field at point P. And this one is actually a little bit easier to see, that when we take the limit, as we see that y becomes much bigger than d. And again, not that y goes to infinity, because then this drops to 0, but just that we have a big y compared to d, so that we're like basically here, there's some plus, there's some minus, and then we're very far away, right? Y is much, much greater than D. So we're far away from it, but hasn't yet dropped to 0. Then what we see is that this term, y squared plus d squared over 4 to the 3/2, actually the d squared term basically goes to 0, and we have over here a y squared to the 3/2, which is actually just equal to y cubed. So we have a similar result to what we saw before. So what we see is that E total at point Q on the perpendicular bisector is going to be equal to negative KQD over y cubed x hat for far away. So for y much greater than d. So when you're far away, but it's not quite equal to 0 yet. So again, this is going to drop off as 1 over y cubed, just like it dropped off as 1 over x cubed before. So it's going as the scale 1 over r cubed for the dipole behavior, so that you can tell it's a dipole, and that we got the same result whether or not we were looking on its perpendicular axis that we just solved for along here, or if we were looking along its axis through the line of the dipole itself. We get this 1 over r squared characteristic dipole electric field behavior. And so this is a nice example of what the electric field of the dipole looks like. And it's also just a really good example in practice with using our definition of electric field for point charges and adding those vectors, just like we add all of our other vectors.